Previously, we built from the idea of an origin through the concept of displacement. Once we have an origin, we know where we are. We can have a position which will allow us to measure from the origin to where we are. Once we have that idea, we can move around, giving us the idea of displacement. Armed with this, we are capable of creating a graph. Because objects don't stay where they are, and I'm going to go down to one-dimensional motion here, we're simply going to have a straight line motion. But armed with this, I can create a graph which tells me, so here's my grid, the position of an object, which we're going to measure in meters for ease of use, at any given time, which we're going to measure in seconds. This is called a position time graph, which we write position dash time, which we can intuitively read position versus time. How does the position change as time changes? And if we take a very simple case, right? The object begins somewhere and moves in a straight line. I can label this up. I'm going to choose a very simple case here where our scale is simply 1, 2, 3. There's 1 second, there's 2 seconds, there's 3 seconds. Okay, so it's a very simple case. The object is moving in the positive direction. That's actually more loaded than you would think. If we look at the displacement between any 2 points, okay, so I can answer the question, what is the displacement from 2 seconds, or from 1 second to 2 seconds? Well, displacement is the concept of change in position. So I take the position at 2 seconds and subtract off the position at 1 second, and that gives me my displacement. Well, I can read my graph and find these things. My position at 2 seconds is here, 3 meters. My position at 1 second is 2 meters, giving me a displacement of 1 meter. So the displacement from 1 to 2 seconds is 1 meter. It's positive. My position is increasing over time, so I end up with a positive displacement. If I had a negative displacement and we did this same problem, or if we had a negative slope this way, my displacement would be negative. Now with this idea of displacement, and looking at this graph, we notice something. It's a straight line. Well, what does it mean that it's a straight line? The slope is not changing. That is the definition of a straight line. The slope does not change. The slopes of graphs have meaning, at least for physics graphs. The slopes all have meanings. So let's look at what the slope of this thing means. So we're going to take the slope of this graph. Slope is y2 minus y1 over x2 minus x1. I'm going to pick 2 points. I have 2 points, I just spoke about them. My second y value is 3 meters. That happened at 2 seconds. My first position I'm going to use is 2 meters. That happened at 1 second. So I take my 2 points, plug them into my slope equation, and I find that my slope is 1 meter over 1 second, which is to say 1 meter per second. Interpret this. For every 1 second, the object moves 1 meter. That is how we interpret this slope. 1 meter in each second. This has a name. We call this idea velocity. This concept of how far does the object travel in each unit of time is called velocity. Very specifically, velocity, the symbol, it is a vector, So we use v for velocity. It's a vector, so we put a hat on top of it. It is a vector. We define this to be the slope of the position time graph. That is the definition. The meaning, or the practical definition, that's the technical definition. The practical definition is how far, there's actually more to that, how far and in which direction does an object travel in 1 unit of time. That is our practical definition of velocity. They're important pieces. How far, the distance the object travels, in which direction, direction matters, in 1 unit of time. It has an equation. Velocity has an equation. It's the slope equation. This definition I'm going to write here is specific to constant velocity. Okay. For right now, we're talking about constant velocity, so here's the definition. Slope. It is the slope of the position time graph. In our position time graph, looking back, when we find the slope, we're finding the change in y values. That's position. Change in position, which has a name. Displacement. Change in position over, going back to our definition, change in our x value, well, that's time. Change in time. Change in position, which is displacement, divided by change in time. For constant velocity, this is the equation. It is the slope formula. This also works always for what we call average velocity. That is the symbol for velocity, for average velocity. Okay, so that is average velocity, or over a given span of time, how fast was, or what was the velocity of the object on average. And that's a very sensible thing. Objects don't travel at the same speed all of the time. So now we have built up the idea of what is velocity. A couple of cleanup things. There's this idea flying around, which is speed. You're probably, well, you are basically more familiar with this than with velocity, which is very technical, but it turns out that speed is also very technical. This is a scalar. It has a symbol. There's its symbol. Absolute value. This means magnitude. How big? How big is the velocity? That's what this symbol tells us. This is speed in general is the magnitude of the velocity. That's the technical definition. The general definition, or the sort of more practical, useful one, is how far an object moves. Far, notice I'm going to leave out part. This is how far an object moves in 1 unit of time. Notice how I've left out direction. Speed is not a vector, it is a scalar. There is no direction. When you take the magnitude of a vector, you lose the direction information. All you know is how big it is. So all we know now is how far it goes in every 1 unit of time. When you're moving in a straight line at constant velocity, these two ideas are completely indistinguishable. They're equivalent to one another. But as soon as you turn, speed up or slow down, the ideas become distinct once again. So we have the idea of velocity, we have the idea of speed. We need to build up a definition. What do we mean by average speed? The bar means average. That is average speed. We don't have any direction information, so we don't want to look at displacement. What we really want is distance. How far has the object gone in total, divided by the amount of time it has taken the object to go.